cosmological spacetime. So my talk today is all about describing how particles interact and scatter off each other in a cosmological spacetime. So the big picture idea is that we can use cosmology as a new way of probing fundamental high energy physics. Okay, because historically, we of course probed this high energy regime with colliders, particle colliders here on Earth, where you create two particles going in with some momentum, they collide in the middle, and as a result of this high energy collision, they spew out jets of stuff that you catch with your calorimeter. So these are experiments that probe energies up to 10 TeV, but because they're happening here on Earth, inevitably they're taking place in very low gravitational fields, environments with very low space-time curvature. So the idea behind cosmological collider physics is to instead use the very early universe, a period of rapid inflationary expansion around the time of the Big Bang, to instead have particles interact with each other at energies that are much, much higher than anything you could achieve here on Earth. The energy scale of inflation could be as high as 10 to the 13 TeV, so it's a qualitatively new range of energies. But crucially, it's also a qualitatively new range of gravitational field strengths. Here, the space-time is rapidly expanding. You have very large space-time curvatures. And in fact, that leads to qualitatively new effects. For instance, you can create pairs of correlated fluctuations from the vacuum. So what we're looking at in this cartoon here is literally the production of three correlated particles from this strong gravitational field. And because these fluctuations are correlated, when we measure the cosmic microwave background, when we measure photons coming from that early time in the universe's history, we see correlations between the temperature fluctuations in the CMB that are ultimately inherited from these high energy interactions taking place in the early universe. So really my talk today is all about how can we use all of the technology, all of the knowledge that's been developed for terrestrial particle physics over the last few decades, how can we take that and apply it in this cosmological collider setting, apply it to the early universe, and probe this completely new range of energies and space-time curvatures. Now, of course, the main player when we do terrestrial particle physics is this object called the scattering amplitude. It's a complex number, and its mod square tells you about the probability that two particles go in with fixed momentum and emerge with fixed momentum. And what we measure in a collider is something like the cross-section, which morally is this interaction probability integrated over the available phase space, integrated over all of the different momenta that these particles could emerge with. So really the dream here would be to write an analogous object on the cosmological collider side, some complex number which characterizes the probability that you produce correlated fluctuations in the early universe, which ideally would share enough mathematical properties with the terrestrial amplitude that we can borrow a lot of particle physics techniques, but also has the same straightforward connection with what we measure. So in the CMB, we measure n-point correlation functions, how correlated are three different, say, temperature fluctuations in the sky. And we would like to write that as the integral over some phase space of the mod square of this complex number. So this object that we want needs to be observable and also have enough similarities with a particle physics amplitude that we can borrow particle physics techniques. So that's the dream. So let me tell you why that's the dream. Why do we want to have these similarities between the cosmological amplitude and the particle physics terrestrial amplitude? Well, amplitudes are useful for many reasons, but here are three that are going to be important in this talk. The first one is that amplitudes are conceptually very useful. Here's an example of what I mean. Suppose you start with some field theory Lagrangian, some local action, and you do something completely trivial to it, right? You redefine all your fields. This is like changing variables in your path integral. And you know that if you change variables in an integral, it doesn't change anything about the integral, right? So these two Lagrangians should be completely the same physics. You could then do something else. You could do a gauge transformation, and that can make the Lagrangian look superficially different, but we know that that's just some redundancy of description. And then in your action, you can integrate by parts. You can add and subtract total derivatives to this theory, and again, make it look superficially very different, but you know that deep down, all of these different descriptions should be the same physics. Now, one thing that amplitude does for you is it cuts through all of that redundancy, because if I take this family of equivalent Lagrangians and I compute from them something like a scattering amplitude, they all give me exactly the same answer. So the amplitude is a very useful way to discriminate between different theories. And we really need something like that in cosmology, particularly for the early universe, where we've industriously been inventing models of inflation for years. There's a huge number of different models of inflation, and it would be great to have a very efficient way of organizing them, sorting them into ones that are genuinely physically distinct from each other, and ones that just look distinct because they're written in different variables, or you've done some gauge transformation. Okay, now the second useful thing about amplitudes is that they're often much easier to compute than the actual observable cross-section. So the reason that they're easier to compute is that people have been very imaginative and invented a large number of powerful techniques for computing these objects in perturbation theory. So roughly speaking, these techniques fall into kind of two flavors. There are on-shell techniques, which means you consider the momenta of the particles as some real numbers that have a norm fixed by the mass of the field that you're scattering. And that includes basically unitarity-based methods like the optical theorem and generalized unitarity cuts, which gives you a way of taking a complicated Feynman diagram and cutting it into simpler building blocks. It also leads to things like the double copy, where you put together lower spin particles to make higher spin particles, and spinor helicity variables, the Park-Taylor formula. The list here goes on and on. On the other side of the coin, though, we have what are called off-shell techniques, where you consider the momenta of the particles to be complex valued. So there's no longer a constraint that they are equal to m squared. You're now in the complex domain, and that lets you write down useful integral representations for these objects, so-called spectral representations. You can use crossing to move between different scattering channels, and there's a number of interesting recursion formulae, which again build higher point complicated Feynman graphs from simpler, smaller ones. So the upshot of all of this technology is that people have just gone to town on a number of different theories in flat Minkowski spacetime. So if you think about something very supersymmetric, like n=4 super Yang-Mills, the state of the art, roughly speaking, is that we can compute anything up to 6 external legs, up to 8 loops, right? So that's very high orders in perturbation theory, using combinations of all of these different techniques. Something a bit more realistic, if you remove all the supersymmetry, would be QCD. And there, the state of the art is that some of the lower multiplicity amplitudes, like 2-to-1 scattering, that's known up to 4 loops. In the vernacular of this field, it's next to next to next to leading order is sort of where the frontier is at now. So that's an incredible, precision frontier that people are trying to push. And then more recently in general relativity, we've seen similar advances. For instance, if you scatter 2 spinless black holes, consider the 2-to-2 scattering of those, that's what's relevant for the gravitational waveforms that would be measured in LIGO, Virgo, and Cagra. And now we know that scattering amplitude up to 3 loops, which is so-called fourth post-Minkowski order, again, in the terminology of that field. But one thing I really want to highlight is that alongside all of those successes, we have what's going on in the cosmological collider community. When I think about doing this perturbative calculation in inflation, I mean, I'm still trying to wrap my head around this diagram. I would like to understand this Feynman diagram better. There's no loops, it's just tree-level exchange of a massive field. And somehow the state of the art here is elegant representations written down by Daniel and others in this kind of first cosmological bootstrap paper, and then developed in various ways in the last few years. So we're starting to see how to even write down this diagram in a useful way, but there's still lots of unanswered questions to do with its analytic structure, and to see how we might build something like recursion relations or more advanced technology that would let us go beyond this to think about more involved, higher order contributions in perturbation theory. So that's kind of one motivation for developing a scattering amplitude for cosmology. And then the final motivation is that amplitudes are an important discovery channel. What I mean by that is they're an important way to discover new heavy states and their properties. So this is a cartoon that I'm personally very fond of. The idea is that at very high energies, there's some fundamental, detailed, high energy ultraviolet physics. And if you knew this theory, you could compute the fundamental scattering amplitude that describes our universe. But in practice, we don't have experimental access to this ultra high energy regime. What we do instead is we measure scattering at very low energies. We build so-called effective field theories that are designed to describe this very low energy scattering. And in terms of the amplitude, really what we're doing is we're doing a Taylor series expansion in powers of the center of mass energy S and the momentum transfer T. These are the Lorentz invariant Mandelstams you can build out of the momenta of the four particles. So what's nice about this cartoon is that in the last few years, we've really developed an increasingly elaborate dictionary between properties that this underlying high energy physics has and the regions of the low energy parameter space that you would probe in a low energy experiment. So the kind of classic example of such a bound is this so-called positivity bound, which tells you the coefficient of S squared has to be a positive number. If the underlying high energy physics is causal, local, and unitary. So ticks very basic QFT boxes. So here I've just cited the snowmass review because that seems like a safe way not to anger anyone by missing them from the slides. This bound comes from 2006 from the famous paper by Adams et al. This is then a field that I've worked on and off over the years, showing that there are also bounds on all of the other CABs, not just 2, 0. And really the state of the art here would be the EFT hedron that Yuting Huang and others have been developing recently, where you get very powerful constraints on all of these EFT coefficients. Now, there's one final aspect of amplitudes that I want to highlight, and this is going to be a little bit more technical, but I find it interesting, and hopefully the experts in the room will find this interesting as well, which is that when we think about how we detect new states in a collider, we often have in mind pictures like this. This is the famous plot from the Atlas detector at the LHC when they discovered the Higgs boson. There's a little bump in the cross-section, and this bump is exactly at the mass where you would expect the Higgs to be. Now, the way to understand why there's a bump, why the amplitude as a function of real center of mass energies that we measure, why does it have a peak? Well, it has a peak because in this complex energy plane, there's a singularity, there's a pole, which corresponds to the exchange of this Higgs boson. Now, that pole is a singularity, and because the singularity is near the real axis, the singularity looks to us like a smooth bump. So that's the kind of picture that I think most of us have in mind when we think about collider physics. But one thing which I find really fascinating is that there is not always a bump. So for instance, if you scatter, say, 2 pions into 2 pions, here's an analogous plot, not of the cross-section, this time of a related quantity called the phase shift. But what I want you to take away from here is that as you crank up the energy, basically nothing happens, nothing happens, nothing happens. And then at around 1000 MeV, there's a sharp kink, there's a sharp spike. And what that means is if you take all that data on the real axis and you analytically continue it into the complex plane, sure enough, you find a pole a little bit away from the real axis at around 1000 MeV. That's the mass of some scalar resonance in chiral perturbation theory. But what's amazing is if you do this analytic continuation carefully, you find that there is another pole in the complex plane. There is another pole which sits happily at about 450 MeV, and that corresponds to another particle, the so-called sigma meson. So it's a bound state in QCD. And what's interesting is that there is no bright Wigner peak. If you measure the phase shift, it was just a completely smooth function, no peaks, no bumps, no wiggles, no features. And the reason is that this pole has such a large imaginary part, it's so far from the real axis that, yeah, although there's a singularity here, by the time you continue all the way to the real axis, it just looks nice and smooth. So what's interesting about this is having this off-shell understanding of amplitudes, being able to go to complex values of the energy, might let us infer the existence of completely new states which we wouldn't be able to see if we just looked at real kinematics, if we just looked for bumps in the cross-section. So that's the kind of opening motivation for why we want to do this cartoon on the right. Why do we want to define something like an amplitude for the cosmological collider? So for the rest of the talk, there's going to be three broad sections. Firstly, I'm going to describe this problem in a much simpler setting of just one-dimensional quantum mechanics. Okay? And the idea here is to do the most basic possible thing, which illustrates some of the key conceptual difficulties with extending scattering technology to non-trivial backgrounds. Then we're going to change gears and do quantum field theory on de Sitter, and I'll talk about this de Sitter S matrix that I recently defined with Guy Pimentel. And then a final section about how we take this on-shell S matrix that we defined and how do we push it off-shell to complex values of the kinematics. Okay, very good. So here is the simple toy model. I am going to describe to you solutions to the time-independent Schrödinger equation. Now, we know that if the potential in this equation was zero, and I just had a free particle. Oh yeah, go ahead.
Yeah, I think there's a question from Angaran. Maybe you can
go for it. Yeah, please. Yeah, now is a good time before I launch into the toy model. Go ahead, Angaran.
Yeah. Hi, Scott. One question I want to ask, when you say going off shell, are we talking about specifically the external kinematics, or are we also saying off shell about the internal energies as well?
Yeah, very good. So when I say off shell here, I mean this amplitude is going to be a function of the external momenta that you throw in, and you might want to consider those to be complex variables and see what happens. Now, of course, the internal kinematics, those are not something that you get to control from the outside. They're ultimately fixed by momentum conservation at each vertex.
Right. And the other question I want to ask as well, because you were saying that these amplitudes are generally, as you said, field redefinition invariant, or at least the cross section, and well, yeah, the amplitude is, and gauge invariant. In when it comes to the de Sitter wave function, we have these like holographic renormalization terms that pop up. Does the S matrix picture basically remove that? Because those seem to correspond to like counter terms, which are like local or non-local, basically, depending.
Okay. So I'll stop you there. So there's lots of interesting points that you want to make in this question. So maybe the first thing I'll say is about field redefinitions and invariance under total derivatives. Yes, where we're heading is an object that is going to be manifestly invariant under all of those redundancies. And I'm going to show how it's related to something like the wave function. If you want to relate it to the wave function, you need to pick a field basis. You need to tell me what are the fields that you're using basically to write down this wave function, right? The wave function is a functional of some fields phi. And if you tell me what phi is, then I can go from the S matrix to the wave function. So that's where this extra information comes in. We know that the wave function is not invariant under field redefinitions, and that's because your choice of field basis is not going to be invariant under field redefinitions. Okay, fantastic. So to come back to this toy model, right? So here I'm hopefully telling you something very basic, which is if you turn off the potential, what are the solutions to this equation? Well, the energy eigenstates are either a particle moving to the right, it's a plane wave, e to the ikx, or a particle moving to the left, e to the minus ikx. So this lets us formulate the kind of canonical scattering problem, where we think of the potential as being some small perturbation around zero. Right? These small wiggles represent this perturbation. What I can do then is send in my plane wave solution, which is a good solution when I'm far away from the perturbation. When it impinges on the potential, there's some probability that it gets transmitted, that's this coefficient t, and there's some probability that it gets reflected, that's this coefficient r. Now, of course, these perturbations are not always symmetric. Delta V could have very different scattering behavior if I scatter from the left or from the right. So in general, I have four complex numbers, TR, T prime, and R prime, which completely characterize how plane waves scatter off of this potential. So a convenient way to put that information together is to write down a 2x2 matrix, an S matrix of these reflection and transmission coefficients. So this 2x2 matrix has many useful properties. So let me name just three. So the first useful property is because of how we've constructed this object, if I turn the perturbations off, if I turn the potential off, then the transmission coefficients become 1. These plane waves just happily propagate without reflecting off anything. The reflection coefficients are 0. And what that means is this matrix, this S matrix, has a piece that looks like the identity, which is just free propagation. And then all of the effects of the potential are all bundled up into some perturbation away from the identity, which we call the scattering amplitude. So this is the A that was in my opening motivation. If you like, it's the interacting part of the S matrix. Another useful property, this is why we collect it into a matrix, is that this matrix turns out to be unitary. If I ask that the total probability of reflection plus transmission, that has to be 1. That's the same as saying that this is a unitary matrix. Or in terms of the scattering amplitude, if I plug in the top equation into the bottom equation, it tells me that the imaginary part of the amplitude is a positive number. And ultimately, that's where these positivity bounds on effective field theory coefficients come from, the fact that C2, 0, the coefficient of S squared has to be positive. That's really just coming from a condition like this. And then the final condition is analyticity. So it turns out that these S matrices, they're a function of K, the momentum of the plane waves you're chucking into the system. And if you think of them in the complex K plane, it turns out they're constrained to only have singularities in the upper half of the complex K plane. You can show that they must be analytic in the lower half. Very good. And I'll kind of skip over the rough derivation. If you want to kind of prove this, a convenient way to do it is to write down something like a propagator, which would be the general solution of the Schrodinger equation for generic source delta V, and study the analytic behavior of this propagator. But those are kind of a grab bag of interesting properties, right, that the standard S matrix has when you do scattering on a flat potential, when V is 0. But of course, not all potentials are flat. In fact, if we want to do cosmology, we will frequently encounter potentials that look more like this. Potentials that are, say, minus some constant divided by x squared. So this is now a potential which, if you're very far from the origin, then if this potential is unimportant and you have the usual right and left traveling plane waves that you had before. But if you get very close to the origin, then this potential becomes incredibly important. In fact, it becomes much more important than the energy term on the right-hand side of the Schrodinger equation. So what you find instead of plane waves, you get these power law solutions where the exponent in the power law is fixed by the strength of the potential. And again, you can organize them into right and left moving eigenstates. So we're going to describe scattering now on this background. And the idea then when we transition to talk about de Sitter is that morally, this is like the Wick rotation of the de Sitter problem. In de Sitter, I have an expanding space-time background where the conformal factor is literally going to be 1 over t squared, where t is time. Okay, so if I want to do scattering on a background like this, I proceed as before. I take my background and I add some small perturbation. And again, I can scatter waves coming in from the left. From the left, I would use these right-moving power law solutions, and I ask what's the probability they get transmitted, so they come out at infinity like a plane wave, and what's the probability that they get reflected, they bounce back as a power law. And I can ask the conjugate question, which is scattering waves from the right. There's some probability they get transmitted as a power law, and some probability they get reflected as a plane wave. So as before, we have 4 complex coefficients that completely characterize scattering from this potential, and I can organize them into a 2x2 matrix. Okay, so far so good. That seems to be a kind of naive extension of what we would do on a flat background. But now there's some important differences that this object has compared to the flat background. The first important difference is that if you turn the interactions off, so if you turn this red perturbation, delta V, if you turn it off, this matrix does not become the identity. It does not become the identity because there is a probability that an ingoing plane wave will scatter off of the background. You can see this very explicitly because if I turn off the perturbations, the Schrodinger equation I can solve exactly. If I send in this as my boundary condition, the exact solution is some Hankel function. And for people that know about the small x expansion of Hankel functions, a Hankel function contains a linear superposition of both right and left moving power laws. So what happens to this S matrix is, even in the free theory, it's non-trivial. And in the cosmological context, this is basically capturing particle production. This is capturing a physical effect, which is that I can start with, say, one particle or no particles or n particles going into my system, and the number of particles that come out at the end can be different. So that's the first important difference. So as we'll see when we do the de Sitter S matrix, that actually spoils some of these nice properties, right? For instance, an S matrix like this, the S twiddle, is no longer an analytic function in the lower half of the complex K plane. So it loses some of the nice features that we might want an S matrix to have. So there's a very simple fix. And the simple fix is what's called in this literature a Bogoliubov transformation, which ultimately corresponds to, instead of using left and right moving power laws as your basis of out functions, you can instead use what I'll call F plus and F minus, which are this precise linear combination of left and right movers, which you get by freely evolving a left moving state from large X. So this is just basically like a rotation. It's a different choice of basis for my S matrix. The scattering problem now looks like this. I'm asking, what is the probability if I send in one of these F plus combinations from the left? What's the probability it gets transmitted as a plane wave or reflected as this conjugate combination F minus? And now these coefficients, the T and the R's without the twiddles, that gives me an alternative S matrix, which actually now preserves a lot of the expected properties, a lot of the things that I would want an S matrix to do. For instance, if I turn off the delta V wiggles, then sure enough, this, by construction, this matrix becomes the identity, because I've literally defined T and R to be with respect to what the free theory evolution would look like. And that means I can split, as before, very cleanly into a trivial interacting piece, a trivial free propagating piece, plus the non-trivial interactions, which are encoded in some amplitude. Now you also have unitarity. So these complex numbers, their mod squares sum to 1. So again, S is a unitary object, and this amplitude has a positive imaginary part. And finally, this S matrix has the same analyticity that we would expect, namely that in the lower half of the complex K plane, it doesn't have any poles. Fantastic. So the summary of this part of the talk is that when you have a background, so when you have a potential that doesn't vanish at the boundaries of your scattering problem, then you have a choice to make. You can either consider scattering left or right moving eigenstates. That would give you this object, the S with a twiddle. And for some questions, this is the object you would want to use. If you want to study particle production, if you want to study how a plane wave kind of transmutes into a power law, then you would compute this object. But if there are other things you want to study, like you want to isolate the perturbations, separate them from the background, if you want to exploit things like analyticity, it can be more convenient to instead choose a different basis, which are namely the free energy eigenstates. So these F plus and F minus, which is a combination of left and right movers, which you get by free evolving a plane wave. And with respect to that basis, you get an S matrix, which behaves in many ways like the flat S matrix that you know and love. So that's about it for the toy model. The next part of the talk is going to be describing how we can use those lessons to describe scattering on de Sitter. So are there any questions about the simple quantum mechanical toy model that we've been discussing so far? Brilliant. So now we're going to shift gears and we're going to talk about quantum field theory on a rigid de Sitter background. So I have in mind now d spatial dimensions. It turns out that the exact value of d is not going to matter. It can be any integer. And the metric, the background metric for my de Sitter spacetime, I'm going to write in conformal time, tau, like this. Now you see that the scale factor that multiplies an otherwise flat Minkowski metric, is precisely 1 over tau squared. So this is why we just considered a potential that goes like 1 over x squared. It's morally the same picture, the same cartoon that we have of the early universe. In the early universe, we have this rapidly expanding spacetime where the scale factor basically diverges like 1 over tau squared as you go to late times, which are conformal time tau equals 0. Now, to orient you, right, tau equals 0 morally is the end of inflation. We want to know what are the correlations at this late time, because that's what gets imprinted in the CMB. And tau goes to minus infinity is morally a very early time where we expect the universe was in some kind of vacuum state. So now we want to consider what happens if I have a scalar field, if I have scalar fluctuations on this space-time background. How do I characterize, how do I discuss their scattering? So in particular, we have in mind the scalar field satisfies an equation of motion, which is the Laplacian on this de Sitter background is equal to a linear mass term, and then plus the interactions. So the interactions I'll just write as some source term j. Now, as before, if we turn off the interactions, if j is 0, then this is a simple linear equation. It's exactly solvable. And you can check what the time dependence of your particle eigenstates would be. And you find the analogous behavior that at very early times, right, this 1 over tau squared becomes unimportant. The space-time basically behaves like it's flat Minkowski space. So a particle moving forwards in time is described by an e to the I k tau time dependence, and a particle moving backwards in time is the complex conjugate. But when you go to late times, towards the end of inflation, then this conformal factor becomes very important, and instead particles moving forwards or backwards in time correspond to power law solutions in tau. So here in this box at the bottom, I want to make a bit more precise what this cartoon actually means. So what do I mean when I say that the time dependence of a particle eigenstate is e to the I k tau? Really what I mean is, if you hand me this scalar operator phi, it depends on tau and k, the spatial momentum. And what I can do with this field is I can separate it, I can split it into two operators, an A and an A dagger, in standard canonical quantization. And how I split the time-dependent field is I need to pick a mode function, this f. I need to pick a solution to the free equations of motion, which are going to basically capture the time dependence of my scalar field operator. So f has to satisfy the equations of motion, but I can supply any boundary conditions that I like for f. So in particular, if I supply the plane wave boundary conditions in the far past, if I say that f in the far past looks like a plane wave, that's one choice, that's one definition of an A and an A dagger, which conveniently corresponds to the A that annihilates the ground state in the far past. So this ground state in the far past is often called the Bunch-Davies vacuum. But I can make other choices, right? I could choose a different set of mode functions. I could choose the time dependence of f to be some power law in tau, and that gives me a different annihilation operator, which annihilates a different ground state. It annihilates the ground state at late times when tau goes to 0. So another way to say that is if you have an annihilation operator, then its conjugate is the thing that creates particles. So if you want to know what is the n particle energy eigenstate at early times, it's the repeated application of a bunch of A daggers acting on the Bunch-Davies vacuum that would define a state which I'm going to call n comma minus infinity. N tells you how many particles you have, and minus infinity reminds you that it's at very early times that we're counting these particles. And a qualitatively different state is if you instead gave me these power law mode functions and I extracted the corresponding creation operator, that would be defining a different state, which is having n particles as measured by an observer at very late times. So armed with these two states, the simplest S matrix you might consider would be what we named in the paper the Unruh de Witt S matrix. It's the overlap between these in and out states. And the reason that we called it the Unruh de Witt S matrix is that if I draw a little cartoon of what it represents, it literally represents the probability that you start with exactly two particles as measured by an Unruh de Witt detector. If you had a Geiger counter in the early universe, it would click twice. Then you evolve that forwards in time, and you want to know the probability that at late times, if you had a Geiger counter, it would still click twice. So you want to know how likely you are to transition from a particle eigenstate to another instantaneous particle eigenstate. But as the notation would suggest, this object doesn't quite share the properties that we might have expected naively of an S matrix. Crucially, it does not reduce to the identity in the free theory. And the reason is ultimately the same as before, that the plane waves that we send in, for instance, they can scatter off the background. Another way to say that in more cosmology language is that suppose you did start with a state that had two particles, even when there are no interactions whatsoever, right? So these two particles just propagate through space-time. They don't talk to each other. They fly past each other. I'm still not going to end up with just two particles at late times because I can pair produce correlated fluctuations from the vacuum. If I time evolve in the free theory an initially two-particle state, it will end up as a state that has two particles plus a correlated sea of Gaussian noise. So it's just like we saw before, you can solve this linear equation exactly. The solutions with these boundary conditions, again, turn out to be Hankel functions. And so if you expand them at late times, you see that there is the same behavior, that an initial particle can turn into some superposition of particle and antiparticle. So particle number is not conserved on de Sitter. And what that means is this overlap, this Unruh de Witt S matrix, even in the free theory, it's non-zero for any 2 to n transition, where n is any even number. And that has some unfortunate consequences. One consequence is that if you roll your sleeve up and compute something like the probability that you go from 1 to 2 particles, you find that this object has two singularities in the complex plane. If I continue K1 to complex values, I find that it has both the pole in the upper half of the complex plane, like I might expect, but it has a conjugate pole in the lower half of the complex plane, which is now spoiling this otherwise analytic structure I expected from flat space. But of course, this is easily fixed, right? We know how to fix this now. What we should do is we should take the free evolution of my two-particle state, and I should use that to define in and out states in the interacting theory. In particular, when I write the state 2 minus infinity in, this is the state that coincides with the free state at early times. But I can define an out state using the late time evolution of my free state. So I can define a state 2 comma minus infinity out. This is basically the two particles that are labeled here, plus a sea of Gaussian noise that would have been created just by the free background expansion of my spacetime. So by using these asymptotic states, what we're doing is a rotation, a Bogoliubov transformation, which defines a new set of S matrix elements, which we call the Bunch-Davies S matrix. We gave it this name because these n and n prime particle states, they know only about the Bunch-Davies vacuum. So these are particle excitations on top of the vacuum at minus infinity. And you don't need to appeal to any other ground state, any other alpha vacuum in the theory in order to define this object. Very good. So here's the cartoon of what it would look like. You're now asking what is the probability that these two particles go in?
Hello, Scott.
Yeah,
sorry to interrupt. So
do.
in the usual Minkowski scattering, we usually assume this kind of stability of the vacuum, which is that vacuum it scatters the vacuum. And this is in Minkowski. This is guaranteed by Poincare symmetry.
That's right.
This cosmological setup, because of the time expansion, the vacuum does not stay instantaneous vacuum anymore. So there's this choice of like out particles, that this Bogoliubov combination that automatically solve that issue for like any cosmological expansion background.
Brilliant.
So
okay.
Whatever you do, you choose the initial.
Yeah, perfect. I couldn't have put it better myself. So on Minkowski, there isn't really a choice of your asymptotic states because, like you said, the vacuum is unique. There is a Lorentz invariant vacuum. And so you would define particle eigenstates on top of that vacuum. Another way to say it is that the ground state doesn't change with time because energy is conserved. Here, as you pointed out, a ground state at one time evolves into some excited state at later times. And so what that means is you now have a choice to make about which ground state you are going to use. So here, the difference between these two S matrices is we've just made different choices for which ground state we are going to use. So I suppose it resolves the ambiguity in one sense. It resolves the ambiguity just in as much as we have made a choice. And so sometimes when people say there is no S matrix on de Sitter because there isn't a unique ground state, I would interpret that as saying there isn't a unique basis in which to express the S matrix. That's how I would interpret that criticism. And what we're saying here is yes, we agree that there isn't a unique basis, but we can start to enumerate possible bases and compute the S matrices in each basis and see what kinds of properties they have and see which one might be the most relevant for any given problem.
Okay,
So
thank you.
a very good question, because now I want to describe why you might use this basis. So why would you use the Bunch-Davies basis? You would use the Bunch-Davies basis because now the particle production from the free evolution that you understand, you can quantize the free theory exactly. So what you've done is you've bundled up that free particle production into the asymptotic states. So what that means is now in the free theory, this S matrix is trivial. And then the interactions lead to some amplitude, some scattering amplitude, which has very simple unitarity and positivity properties. This object as a function of complex K also turns out to be analytic in the lower half of the complex K plane. You've effectively removed what would otherwise be a conjugate pole in the lower half plane. So if you want to play these games with off-shell techniques or exploit things like unitarity and positivity, it seems to us at this stage that using this Bunch-Davies S matrix might be the better choice. But of course, they're ultimately just two different choices. And because they're related by some rotation of your bases, I would say they are at some level physically equivalent. It's just mathematically which is going to be the cleanest object for deriving things like unitarity conditions or analyticity constraints.
Sorry, there's
Okay.
another question by
Yes,
Angaran.
please. Go ahead.
Hi Scott. So just to clarify, is the fact that the Bunch-Davies vacuum looks like the Minkowski vacuum in short scales the important aspect of this? And the other is a related point that I want to ask is in these like chemical potential theories, we like modify how the Bunch-Davies vacuum looks in a way that it on short scales where it doesn't look like a Lorentz invariant Minkowski vacuum. Would these kind of theories be screwing up this analyticity property in the law?
Very good. Thank you, Angwer. That's a great question. So the first part of your question was about is this related to choosing Bunch-Davies over some alpha vacuum? And for those that are familiar with alpha vacua, you might not be at all surprised that for S twiddle, which used the vacuum at late times, that's ultimately some alpha vacuum, that has multiple poles in the complex plane. We know that if you don't have Bunch-Davies somewhere in your calculation, you're probably going to generate these kind of folded, like unphysical singularities. So this is just the kind of S matrix manifestation of that if you can define an object using only the Bunch-Davies vacuum, you have a much simpler analytic structure. Now, the second part of your question was what happens when you put all this at a finite chemical potential? That's a good question. I don't know. So ask me again at the end and we can discuss that. Here I'm talking about a simpler setup where this is just a free scalar field phi, and then with some interactions that I can treat perturbatively.
Oh, thank you.
So let me explain how. So I'm going to give some examples of computing these S matrix elements now. But before I do, let me prove that as advertised, these objects are related in a simple way to what we observe in the CMB. So if you're interested in measuring, say, how correlated three fluctuations are in the CMB, it's effectively asking how correlated are three insertions of this field phi, which you can write as an integral over all field configurations at late times of some probability, the mod square of the wave function. This is the probability that the universe ends inflation in the field configuration phi. So you integrate over all phi 1, phi 2, phi 3, weighted by the probability that you are in that state. Now, it's common to parameterize this wave function as an exponential. You write it as the exponential of a sum of so-called wave function coefficients, psi n, which multiply n phis. Now, mathematically, you do this because the wave function is really a functional. It depends on field configurations, phi. It's much easier to deal with functions. The psi n are just simple functions of the n spatial momenta. Physically, the reason that we do this parameterization is that we know that when the interactions are very small, then what emerges at the end of inflation is typically very close to Gaussian. So what that means is when you have small interactions, this psi2, the coefficient that sets the width of your Gaussian, that's much bigger than psi3, which is the coefficient that sets, the skewness, and that's much bigger than psi4, which is the so-called kurtosis. These are kind of non-Gaussian corrections, that psi's with n bigger than 2, and you can treat them perturbatively when the interactions are small. So this is one parameterization that you can use to compute the psi n, and therefore compute the correlations that you measure at the end of inflation. But now the crucial observation here is that what is this wave function in terms of bras and cats in my Hilbert space? Really, this wave function is asking the question, what happens if I start in the Bunch-Davies state at very early times, and I let it evolve, and I project onto a field eigenstate at late times? Okay, so it's the overlap of a particle eigenstate with a field eigenstate. But since I have a complete basis of n particle states, I should be able to expand a field eigenstate as a sum of n particle eigenstates with some coefficients. So if I plug that expansion into the definition of my wave function, and I massage it a little bit to extract these psi n coefficients, what I find is that these psi n's are linear combinations of 0 to j S matrix elements. Now, the coefficients that appear in this expansion are known. We write them very explicitly in the paper. The important thing is that they're model independent. So all of the dynamical information, all of the interactions, they're encoded in your S matrix. And then these B coefficients are just some kinematics. It's just some kinematic factor, which is mapping one to the other. And crucially, these B's depend on the basis of fields that you use. So you might ask, well, I thought you said this S was supposed to be invariant under field redefinitions, but we know that the psi's are not. And the reason is that these kinematic conversion factors, they depend on the field basis that you choose. So it's these B's that are responsible for the psi's not being field redefinition invariant. The other thing that you might notice is that if you just give me the set of psi n's, that's not quite giving me all of the S matrix elements. It's only giving me the ones where I transition from the vacuum to J particles. There are other S matrix elements that I can consider when I have some particles in the far past, as well as in the far future. And so those are important when trying to construct things like unitarity relations. We'll come back to that in a moment. But now to kind of wrap up this slide, what I want to stress in the box at the top is that, as promised, if you want to compute something like an n-point correlation function from an S matrix, well, we know it's the mod square of the wave function, and I've told you the wave function is linearly related to the S matrix. So ultimately, you can write a correlator as a sum of S matrix times its conjugate. So this is morally the promised relation, that these C's are some integrals over some phase space factors, but ultimately, if you know all the 0 to j S matrix elements, you can take their mod square and extract something like a correlator. Okay, good. So for the rest of the talk, we're going to describe properties of these S matrix elements. And you should keep in the back of your mind that if you wanted, you could turn the crank and work out the corresponding observable for the CMB. So the final part of the talk is about what these S matrix elements look like if you start going to...
Scott, I think there's a question by Yutin.
Oh yeah, great. Thanks, Yutin. Go ahead.
Sorry, maybe I missed this, but can I ask if the sum over J, is that an infinite sum, or is that like depend on n is bounded?
Oh, very good. Yes. Okay, that's good. So these J's, they start at n, but then go to infinity. Now, the important thing here is that in perturbation theory, when you go to higher and higher multiplicity amplitudes, they are suppressed by more and more powers of the coupling. So actually, that's what this example at the bottom was supposed to illustrate, that in practice, these expressions are exact. You have to do an infinite sum over all the S matrices up to an arbitrary number of particles. But in perturbation theory, this sum truncates at whatever order you truncate your perturbative expansion. So in fact, you can think of, say, the 0 to 4 S matrix. It turns out to be a linear combination of just the 4-point wave function and the 6-point wave function coefficients. And the higher order stuff is suppressed by more powers of the coupling.
Okay, thanks.
Okay, fantastic. Great. So the final part of the talk is about what happens when we take the story and push it off shell.
Scott, could I ask one more quick question?
Since you asked a couple already,
Sorry.
Could I postpone your question to the end? So got about 5 minutes or so, and it'll let me finish this off-shell section, and then you can ask at the end. Okay. Thanks, Ankaran. Right. So the way that we're going to go off-shell is a bit like on flat space. You can ask, what does going on shell even mean? Why are these S matrix elements on shell objects? Well, the reason that they're on shell objects is that you can formulate them as an LSZ reduction of time-ordered correlators. Okay. So what you can do on de Sitter is you can compute the time-ordered correlation function of n fields at unequal times. You can hit each of these fields with the free equations of motion. That's what this epsilon is. It's the equation of motion operator. And you should have one equation of motion operator acting on each field. And then that's amputating the external legs. And then you should put those amputated legs on shell, which means you should integrate over these mode functions, these Hankel functions, F+. Now, again, there's one Hankel function, there's one integral for each one of these n times. So that is, if you like, the LSZ way of computing these S matrix elements. And it's exactly like what you do on Minkowski, but really you've just replaced the usual free mode functions with some complicated Hankel functions. Now, one useful way to think about this reduction procedure is that you're really doing 2 steps. The first step is you're taking the amputated correlation function, and you can do the usual kind of Minkowski transformation where you Fourier transform from conformal time to some energy variable omega. So if you do that step, that's just some integral transform. And now every field is labeled by a so-called off-shell momentum. It's labeled by both its spatial momentum and this conjugate parameter omega, which is conjugate to whatever time you inserted it in the bulk. Now that's, of course, not quite an S matrix, because we haven't used Hankel functions anywhere. So the second step would be to then take this amputated correlator, and you can do a Fourier transform with respect to this angular variable rho. The idea is you replace, if you want to go on shell, usually on Minkowski, that's just replacing the energy with like the square root of k squared plus m squared. It's just some analytic replacement. On de Sitter, if you want to go on shell, it's an integral transform. You replace the energy with k cosh rho, and you integrate over all rho. Now, physically, this makes sense. Rho is basically the Schwinger proper time that this particle experiences. And since energy is not conserved, what you're doing is you're saying that this particle has some energy k, maybe now, but then you should integrate over all proper time to account for all blue shifted energies that it could have had in the past. And that's what this transformation is doing. Okay. So what we found is that these off-shell objects, these amputated correlators, are shockingly simple. They're very simple functions of these off-shell momenta. And all of the complications, all of the hypergeometric functions that we usually encounter in cosmological collider physics, they all come from doing this final step where you put the particles on shell. Now that's important because somehow going on shell is ultimately a kinematic step. Going on shell is to do with how you treat the asymptotic propagation of basically free particles. All of the interactions, all of the dynamical information is encoded in these off-shell correlators. So what we want to do now is compute these off-shell correlators because they are much simpler object, which gives us a handle on really what's going on kind of underneath all of the special function madness that often plagues these cosmological collider calculations. So there's 2 things I want to tell you about these amputated correlators. The first one is that you can ask, well, what do they look like in simple examples? If I give you lambda phi to the 4, that's my interaction. and I compute this correlator. On Minkowski, it's very simple. I mean, it's fixed by symmetry to just be an energy and a momentum conserving delta function. Now on de Sitter, it's also basically fixed by symmetry. It has to be a spatial momentum conserving delta function, and then a total energy pole where the power of this pole is fixed by dilation invariance. Then you could ask, what happens if I have contact interactions with derivatives? If I sprinkle in some derivatives, on Minkowski, this is basically trivial in momentum space because every partial derivative of phi just becomes a factor of the covariant momentum p. But on de Sitter, what we find is that we get the Minkowski answer, p1.p2, but then plus a bunch of corrections. And this pattern turns out to be super general, that if you give me any interaction with any number of derivatives hitting these fields, on Minkowski, it would be easy to write down the answer. And on de Sitter, you basically get the Minkowski answer. This has been known for a long time, that the kind of residue of the total energy pole is somehow the Minkowski answer, plus corrections. Now, the way to think about these corrections is they're basically coming from expanding these covariant derivatives as partial derivatives plus Christoffel symbols, right? So these are coming from the curvature of the background spacetime. So these curvature corrections are actually very easy to predict. They're easy to predict because if you're on a de Sitter spacetime, everything's maximally symmetric. They have very simple commutation relations. So what we were able to do is write down a differential operator, p hat. It's a differential operator which is defined by two properties. When it hits your plane wave mode functions, it just gives you the usual kind of omega k 4 vector from flat space. But because it has derivatives in it, it doesn't commute. And in fact, if you commute 3 of them, you precisely reproduce the commutation relations of the covariant derivative. And why this object is nice is that now you have very simple Feynman rules. Anytime you have an interaction in the Lagrangian, you just replace all the covariant derivatives with a factor of p hat. And the fact that they don't commute basically automatically generates all of those curvature corrections. Now, there are some really remarkable properties of these p hats. It turns out that just like on Minkowski, when the total momentum vanishes and these p have fixed norm when you go on shell, on de Sitter, we have the same properties that if you take the total p hat and you hit any correlator, it vanishes as a consequence basically of the spacetime isometries. And when you go on shell, when you do this integral transformation that I described, that integral transformation replaces every p hat squared, it replaces it with an m squared, a factor of the mass. So you can count invariants, kinematic invariants, you can count in exactly the same way that you count on Minkowski. So Minkowski, we know that the most general tree level amplitude you can possibly have is a contact piece. It's just an analytic sum of S's and T's, plus possibly exchange pieces, which come from diagrams like this that have a simple pole. Turns out on de Sitter, the most general 4-point correlator you can have at tree level takes exactly the same form. It's an infinite sum of these operators, S and T hat, plus possibly some exchange terms. So since I'm running a bit short on time, right, what I want to do is kind of wrap up in the next sort of 60 seconds or so. So what I'm going to do is skip over this slide, which is describing how we go about computing objects like this. If I have S hat and T hat acting on this kind of seed correlator, we have efficient ways of computing it. Really what I want to show you is this final slide, which is the spirit of using these off-shell mode functions is that you're separating what is the dynamical information from the kinematic propagation. And I think this leads to a very nice story, which is that if you consider something like the 0 to 4 S matrix element, which corresponds to a diagram like this. Okay, so this is the cosmological collider signal. If you turn the crank and you turn this S matrix element into a correlator, it has this characteristic oscillatory shape at small momenta ratio. Okay, and of course the goal, the party line, is that if you measure the CMB statistics accurately enough, you would be able to see these wiggles, and their frequency would tell you something about the mass and the spin of the new fields that are around during inflation. Now, the reason that these look like wiggles and are not just simple, bright Wigner peaks is really that you have these factors of these kind of external mode functions that are turning very simple spectral densities, turning very simple functions that just have a pole in the complex plane, they're turning them into something more complicated, some infinite sum of hypergeometric functions. So what I find interesting about this story is that usually we have in mind that cosmological collider physics is about measuring features. If you measure this wiggly feature, you would infer the existence of a new state near the real axis. But if you know how to do these off-shell continuations, if you know how to push all of the story into the complex plane, you can now investigate whether even in perfectly flat signals, suppose you see no features whatsoever, you might still be able to infer the existence of some new heavy state, some new pole, which exists just very far from the real axis. So this is what I've told you about today, right? I wanted to sketch the definition of an S matrix for de Sitter. It has many nice properties. If you're careful with your asymptotic states, it splits into the identity plus some interacting piece, and observables are basically the mod square of this object, which for the bispectrum is very simple. It's ultimately going to be the imaginary part of this amplitude, much like a cross-section. We defined these Mandelstam operators, which give you a very general way of expressing what any kind of four-particle S matrix ought to look like. These amplitudes have simple positivity, unitarity properties. I skipped the part about spectral representations, but that was because I was very excited to tell you about how you might think about these correlators that we're measuring and being pushed into the off-shell complex domain and use that to look for the presence of new states. So here's a to-do list of things I would very much like to see happen in the next few months and years. But what I'll do is wrap up now and take any final questions. Thank you very much for your patience and letting me finish.
Thank you very much. Thank you very much, Scott, for this very nice talk. Actually, I have a question, but maybe I take my question last, so I leave questions for others. So,
Okay.
are there, any questions, please? And maybe also Angaran will also be second to last.
Okay. Yeah, perfect.
Actually, if not, then I get to ask first.
Yeah, go for it.
Maybe because my question was actually to just the previous slides. So kind of this notion that you could detect a particle very far off the real axis, like from the smooth shape.
Yes.
So in what sense, because the smooth shape we were always interpreting as integrating out a very heavy, when the particle becomes very heavy, and you naively integrate it, but not naively, if you integrate it out, you get a series of contact interactions that generates this smooth shape. So in what sense is this not degenerate or the same, maybe even? Like moving very far off the pole, isn't that just a series of contact interactions generated by this massive state?
Yeah, that's a good question. So maybe I should hold my hands up and say that this picture here is of course a little bit idealistic. The idea is that if you had exquisitely accurate measurement of this curve, then what you're really doing is giving me a function on the real axis. And then I can continue that function into the complex plane. Now, I suspect that if you take the infinite series of contact interactions that you mentioned, which come from like local interactions, you could probably continue into the complex plane and you wouldn't see any pole.
Mm-hmm.
But there's a slightly different curve, there's a slightly different function, which when analytically continued, would have a pole. And so here the idea is that if you had precise enough measurements, you would be able to tell the difference between a function on the real axis, which when continued does or does not have a pole in the complex plane. But of course, the caveat here is that if this is what we see in the data, okay, then probably the error bars are going to be sufficiently large that at least in the short term, it's going to be very difficult to do something like this. But I think conceptually, it's important because I certainly found this surprising, right? I always had it in my head. At least I tell people that, if we measure the shape of these wiggles, that's like the kind of, smoking gun. That's what we need to see to learn about new particles. But at least conceptually, it seems like there's this other channel where even if there's no apparent features, the shape of the function might still be such that when analytically continued, you see poles. And that would be a smoking gun of some new heavy state in the early universe.
Okay, thanks.
Okay, thanks.
Any other questions? Maybe from the room? I think there was a question.
How do I raise my hand?
Yeah, go for it. You have a question?
Yeah, can I have a question?
Yeah, please go ahead.
Yeah. In flat space, the offshore effect seems to be able to transfer to high dimensional operators by field redefinition. So
Yes.
in that sense, that there's no ambiguity there.
Perfect. Yeah.
So when you're in curved space, how do you deal with this kind of ambiguity?
Wonderful. Yeah, that's a fantastic question. So rather than jump back and forth through the slides, let me just give you the short answer. So when we talk about these off-shell correlators, they are not invariant under field redefinitions. For exactly the same reason that on Minkowski, when you're off-shell, if you do a field redefinition, this object can change. But what happens on Minkowski is when you go on shell, right, when you set all the p squareds equal to m squared, all of that redundancy vanishes. So you always land on a unique answer.
Right.
So the same thing happens here. So when we write an off-shell amputated correlator, it can depend on, if you do a field redefinition, it will shift by terms that depend on p hat squared minus m squared, right? It'll depend on things that when you go on shell vanish.
Right.
So when I wrote this equation and said, oh, the most general correlator is this, really what I should have said is the most general correlator is this, plus stuff that vanishes when you go on shell. That's important. Yeah. So you can absolutely, the off-shell correlator has these extra redundancies, but what we want to do is kind of, anticipate that when we go on shell to compute something like a correlator, a cosmological correlator, when we go on shell, all of those redundancies are going to get projected away. And what's nice is that we can anticipate which terms are going to get removed in advance. So although we're writing down an off-shell object, if we write it in terms of these p hats, then it's very clear which terms you can throw away. You can throw away anything that contains a p hat squared. Once you actually expand out the p hats and you do all the derivatives and you get a really complicated long expression, then it's much harder to see what you can throw away and what you should keep. So that's one of the virtues of writing it in this kind of language, that you have a clear parallel with what happens on Minkowski.
Okay, thank you.
Okay.
Scott, can you hear me? Or
And yes.
great. So I have a question about the flat space limit, that how that would work. And in particular, is this Mandelstam operator you're using translate to something simple there?
Oh, yeah, fantastic. Thank you so much for asking. I'm so glad you're here. In the flat space limit, these curvature corrections vanish. So exactly, when you take the limit that the Hubble rate goes to 0, S hat and T hat, they become the Mandelstam's S and T from flat space. That's why we use this notation. So on de Sitter, you have these two operators that don't commute, but if you restore all the factors of the Hubble rate, you see that their commutator is proportional to h squared, right? It's proportional to the background curvature. So when you take the flat space limit, the curvature goes away and these operators commute. And in fact, they just become simple functions. They become P1 plus P2 all squared and P1 plus P3 all squared. Yeah, so there's a very real sense in which this has a kind of very natural flat space limit, which ultimately involves just rubbing out all the hats.
Okay. Now,
Okay.
actually,
Yeah. Okay. Thanks.
sorry. Now we have a bunch of questions, but I should check with Scott because you mentioned you have to take off in like 5 minutes from now.
So I actually have a student that's due to come. So actually, I'm happy to take another couple of questions, and at some point a student will arrive, and I'll need to say goodbye. But
Okay.
they're not here yet, so by all means, ask another question.
Okay, I think so. Santiago was the next, then Gordon, and then Angara. So Santiago.
So going back to the flat space limit question by Cameron. So in flat space you have this k1 squared plus k2 squared plus, sorry, s plus t plus u is equal to 4m squared. Do you have something similar here?
Yes, exactly. So I told you that if you sum all of the p hats, like the total p hat vanishes, and that p hat squared is basically m squared. So those are the same conditions that on Minkowski lead to s plus t plus u is equal to 4m squared. So actually the same thing happens here. I didn't write down a u hat, but you could define a third Mandelstam operator, a u hat, which would indeed satisfy the identity that you mentioned, the s plus t plus u, all with hats, is equal to 4m squared.
Great. Thank you so much.
Okay, Gordon, maybe next.
All right, thanks, Scott, for a nice talk. I have a question. So when you talk about analyticity, do you have in mind analyticity in terms of these S hat and T hat? Because I think the P, they are not, they don't compute with each other, right? So how do you understand this?
Oh, brilliant. Yes, exactly. So this is one of the things I would love to understand better. So as you know very well, on Minkowski, the story is you fix T and you analytically continue S to the complex S plane. Now, I do not know how we should think about that operation here. So the natural analogs of S and T seem to be these S hat and T hat, but since they don't commute, they can't be diagonalized simultaneously. So actually, the part of the talk that I skipped is that for, say, an exchange diagram that only depends on S hat, this is morally like 1 over m squared minus S hat, then that's fine because you can just work in eigenstates of S hat. If you only have one of these guys around, you just work in eigenstates of that operator, and that's how you get these simple integral representations. The problem comes when you have more general amplitudes, like the most general amplitude has both an S and a T and a U channel, and it has terms that mix S hat and T hat. Now, there is no convenient eigenbasis in which this is just simple multiplication, and you can only make one of them simple. The other one's going to be complicated. So I don't really know how to think about going into the complex plane for a completely general object. I only know how to do it for single diagrams that depend only on either S hat or T hat, but not both. So that's the big analyticity obstacle that we'd need to overcome to do something more like kind of positivity dispersion relation arguments.
I see. Thank you.
We have a question here.
Yeah, go ahead.
So yeah, I have actually two related questions. The first one is that, so in terms of the time evolution operator, the one involving from far past to the future.
Yeah.
So how is it possible for your S matrix to write this in terms of these the time evolution operators?
Yes, very good. Okay, so you said that's the first part of your question. Let me quickly ask the.
Part is that once I use these. Okay, go ahead.
Yeah, so the first answer is, yeah, I've been writing all of these in like the Heisenberg picture, so there isn't like an explicit U hat in the middle. But of course, there's another way that you could write this in something more like the Schrodinger picture, where you think of taking the Bunch-Davies vacuum in the past, and then you stick in a time evolution operator U, which evolves it into the far future, and then you're projecting onto this state, which lives in the Hilbert space at late times. So yeah, there is a way to write this with a U hat in the middle, which maybe is more familiar because then it looks like the S hat, operator from Minkowski. It's indeed the time evolution from -infinity to 0. Now, now my student has arrived. So if you quickly ask the second question, I'll answer it, but then I'll need to go.
My question is, yeah, I want to see unitarity in terms of S dagger as equal to 1 from this representation.
Say that again, sorry, I didn't quite catch it. What is unitarity?
Unitarity S dagger S equals to 1.
That's right. Yes, that's right. It's U dagger U.
Operators.
Yeah, exactly. In terms of time evolution, that U is a unitary operator. So U dagger U is equal to 1 as an operator. And then if you sandwich this with Braz and Katz, then it becomes ultimately this condition here in terms of the A's. So S is a unitary matrix because U is a unitary time evolution operator.
Okay, thank you.
Yeah, brilliant. All right, thank you so much, everyone, for the great questions. But I will have to take off now. But thank you very much for having me.
Yeah, thanks a lot, Scott, and we will see you in.
Thank you, Scott.